Okay? So the only interesting problem for us are big problems. Justified, if you think about it, by more, right? And sort of the power of processors. Small, so that you have these sort of artifacts about, 1/2 n squared being smaller. When n is that small, you don't need to be smart. You can when you want, and it's solved instantaneously. Okay? So to play when you have non-trivial problem sizes, when n is something that's not tiny. Okay? And of course, as and so do our ambitions, anybody. What are the interesting problem sizes? They're big. Okay? Hundreds, tens of millions, billions. These are the data set sizes we deal with now. Okay? So as time marches on, this focus on the rate of more and more faithful to how computing is executed. This is the bias in CS161. Okay. Worst case analysis, being cavalier about ignoring small constant factors and lower order terms and focusing on rate. Fast algorithm. What do we actually mean? We actually mean running time okay? This is what we're shooting for. Usually the Holy Grail will be, and we will not always achieve this Holy Grail, but we'll usually get close, will be to have an algorithm which runs in linear time. Okay? So meaning that if the input size is n, then the number of operations is no more than a constant times n. So why does that seem like a natural kind of barrier? Why would that be a Holy Grail? That's right. Right. So the comment is, well, you have to at least know what problem you're solving, right? So even to know what problem you're solving, you have to look at it, and its length by definition is n. So usually linear time is an obvious constraint on how fast our algorithm could conceivably be. There are exceptions. I think all of you know at least one algorithm which is better than linear time. You think of one? Yeah. Binary search, right? And that's because actually you know that your input is so you don't actually have the whole thing to solve the problem. Okay? We can do that in log time. But those will be the exceptions. Okay? So usually at 161, we try to design fast algorithms, meaning worst case running time growing linearly or not much worse with the input size. Okay? And I should say, I think this is actually kind of a case study of, the role of theory, the role of mathematics in an engineering discipline like computer science. You start with, real engineering problems you want to understand, like you want a fast algorithm for lots of different important problems. But you don't just want to take shots in the dark, right? You want a principled approach, you want to reason about it, you want to understand why something works. So the point of theory, the point of math practice in this class, you then you discard with what you hope are second-order details, like small constants and lower-order terms. You get an abstraction, worst-case running time, which you can reason about and develop fundamental insight to approach the problem, and that's exactly what this class was for the next 2 months. Now, of course, after solving a problem, you go back and take insights and fine-tune them to the application domain. And like I said, that would be inappropriate to discuss in 161, but there is this final step. Okay, so this is our abstraction. We've thrown away some details, identified the salient features for algorithm design, while first-order insights to problem solving. Okay, so that's what it's about.